Okay, so the last topic here on oil PVT is using DLE data together with the multi-stage separator test data with the purpose of generating tables of black oil PVT properties, which we're going to talk about next week, okay, for engineering calculations. Now, some of you already know what black oil PVT properties are. I'm not going to get too much into that because it's stepping ahead of the material in the course. This is chapter 7. But for practical purposes, all engineering calculations, and I should probably say petroleum engineering calculations, are based on these black oil tables. Those calculations would include on the reservoir side, if you're going to do reservoir engineering, you got what's called material balance, material balance calculations. This is the old school way of treating kind of recovery efficiency of oil and gas from a reservoir by producing it by depletion. So material balance, you've got the rate equations, which tell you how much each well will produce of gas and oil. You've got reservoir simulation, which is the most typical type of engineering we do as reservoir engineers. Reservoir simulation. And all of the equations you find in all of the books that you're going to be doing these things with will use the black oil PVT formulation. Production, flow assurance, pipe flow, I'll just call it pipe flow. Programs like Prosper, which is calculation of pressure loss in production tubing, GAP, or Olga, maybe not Olga, but GAP, calculating pressure losses in surface gathering network systems. You get the well to the surface, and then you gather a bunch of wells together, and you put them in pipelines. So you've got these things. And a lot of these programs, if not all of them, will be using these black oil PVT. So it's a bit old school, still use some. And typically, we're not going to use an equation of state model. So it's not so many situations, but this is. Now, the Appendix D in the book is written by Standing, and I basically took his notes, got it in the nomenclature of the book, and put it, it's basically his notes talking about this topic. So this topic is really covered in detail in Appendix D. It's also covered in Chapter 6. So I'm just going to give you the summary of the equations to go from DLE data together with SEP data to create the so-called black oil PVT. Okay? Just the mechanics of doing that. Okay, the first black oil PVT data we're going to talk about, these are for the oil phase. The oil formation volume factor. RS is the solution gas oil ratio. And then the third property is oil viscosity. Just very briefly, what are these properties? Well, if we're down here at reservoir temperature or at any temperature and pressure, and we have an oil, okay? And let's say that we have a certain volume of that oil, and we take that oil to the surface, okay? And we process that oil through a multi-stage separator. Let's just make it simple, two-stage separation, down to stock tank. 2 stages of separation. So we end up with a surface gas volume and a surface oil volume. Excuse me. Now this could be the original oil at original pressure, or it could be some depleted oil that's together with some gas. Okay? So it might or might not be, it's just, you just take an oil at some pressure and temperature, you calculate its oil volume. So the BO definition is this oil volume at reservoir temperature or whatever temperature and pressure. You're starting the volume divided by the final volume that you get at surface conditions through a multi-stage, some kind of multi-stage separator process. And the RS is defined as the surface gas volume that you get at the surface divided by the surface oil volume. So what we're going to do now is we're going to assume that this process, this is from our lab separator process. Now remember in the chapter 6 we looked at there was four of these two-stage separators, right? And we found out the one with 100 psi G pressure gave the most oil, right? So that's our most efficient two-stage separator. Okay. But the lab sep experiment is of the original oil, right? Okay. But here we're talking about any oil at or below the bubble point. Okay? So from the SEP test, what we get is what we call BOB and RSB. And I think we can go back to the book. We can look at that table again that we looked at earlier, or last week. This one here. And okay, so if we pick this as our optimal separator conditions, then the BOB is this number here. That's the oil volume at the bubble point over that surface oil. And the RSB would be this total gas-oil ratio. There's two gas-oil ratios here, so we have to pick the one that's per stock tank barrel. That's this one here. So that would be 676 plus 92. Both of these are in standard cubic feet per stock tank barrel. So you can add them together. 8, 6, is that right? Okay. This is in, the term for this is, it's either barrels per stock tank barrel, or the SB will also let you write reservoir barrels per stock tank barrel. You can write it either way.
Excuse me?
Yeah.
What's the difference between the first GOR and the second GOR?
Maybe, did I screw up? Yeah, it was these two. Oh, what's the difference between this one and this one?
Yeah, B and C.
Yeah, the B, you can't really see it. I'm going to try to go over here. This B says standard cubic feet of gas per barrel of oil at the separator pressure and temperature. Okay, so this is per barrel at 50 psi. This 737 is standard cubic feet per stock tank barrel. Okay. So now, what we want or need is BO at pressures less than the bubble point, and the amount of gas that's still in solution at pressures less than the bubble point. Because we know the gas-oil ratio at and above the bubble point. That's 768. We know the formation volume factor at the bubble point. But the question is, as we deplete below the bubble point, how does the BO and RS change? That's what we want to estimate. So the standard method to do this, not necessarily the best method, but it's the standard method, is that we take the differential BO from the DLE experiment. Okay, this is from our DLE. Times the bubble point from the separator test. That's the 1.474 number, divided by this differential at the bubble point. This is from the DLE. And this should be approximate. It's not an exact thing. It's only exact at the bubble point.
So this pressure, the range of pressure will be from the initial reservoir pressure, or
No, this will be only from, this is our, okay?
so we will not do any corrections for the bubble.
Yeah, no, this is the only, yeah, this is probably a good point. We want these for saturated oils. Properties. Okay. So let's just go in and find the, we have that differential that differential table up here. Let's just pick a number. 1600. Okay, so at 1600 psi, the differential BO is 1.447, 1.445. So at 1600, is that what it was? The BOD was 1.445. Is that right? I can't remember. 1.445, 1600. And that's in reservoir barrels per what? Residual barrel. Residual barrel. At the bubble point, we have BOD, B, which is equal to what? At the bubble point, 1.6. Reservoir barrels per residual barrel. And also at the bubble point, from the separator test, you've got BOB, and that was 1.474. For stock tank barrel. So the BO that you need for engineering calculations at 1,600 pounds would just be this equation here, the BOD, pressure 1.445 times the BO bubble 1.474, 1.600. Somebody help me? And that's in reservoir barrels per stock tank barrel, if you cancel units. Because the residual barrel here will cancel the residual barrel there. .33. And since we have digits 3 to the right of 1, we can probably take one more. 1? Okay. Yeah. Okay.
What is the equation that you wrote? What is the basis for this equation? Is it empirical or?
I'd say it's empirical. It works pretty well for if your oil has an RSB less than about 1,500 cubic feet per barrel. It's I'm going to put 1,000.
Why do we need to do this? Why can't we just use the differential data directly?
Okay, so you can't use the differential because what the differential is saying, let's just say we're at the bubble point in your reservoir, is that it takes 1.6 reservoir barrels. If you take 1.6 reservoir barrels and you brought it to the surface, you kept the temperature at reservoir temperature and went through this multi-stage process, the differential liberation process, you'd end up with one stock tank barrel. Okay? But we never do the surface processing like that. I mean, what it's telling you is that if you had a surface process that had all of these stages here, how many stages is that? 1, 2, 3, 4, 5, 6, 7, 9, 10, 11 stages plus bleeding, okay? 10 stages plus bleeding. At the surface, all at reservoir temperature, you can imagine how much heat you'd have to put into the system, okay? Then, to get one stock tank sellable oil, you'd have to bring 1.6 barrels out of the reservoir, okay? That's not how we process, okay? That's not how we produce our reservoir. So consequently, what you want to know is how many barrels, reservoir barrels of oil do I need to take out to get one sellable oil? And the sellable oil is going through a separator process like this one with 100 pounds initial pressure at the first stage. Then it only takes 1.474 reservoir barrels to get my one sellable barrel of oil. Okay? It takes less reservoir volume taken out.
But isn't it better to have many stages?
Not at reservoir temperature.
This volume should be higher, no? Like the efficiency, we are saying that if we use the multi-stage separation, the efficiency of the system is more, but we are taking
Okay.
less from oil.
Okay.
You just said temperature.
Okay. So the thing is that the efficiency of the surface process depends on the number of stages and the pressure and temperature at each stage. It's much too complex for me to say what would be better, A or B or C. 3 stages with these conditions or 2 stages with these conditions. There's no way I or anybody else is smart enough to tell you this gives more oil, stock tank sellable oil. It's just too complicated. What I can tell you though is that if you put all of your separator stages at the surface at reservoir temperature, that's not good. Why? Why is that not good? Anybody? The K values. You looked at the K values, right? The K values of the heavy components, which we want to keep in the oil, we want to keep those K values as low as possible, right? To keep those components in the oil. If you increase the temperature, the K values go up. The vapor pressure goes up, K values go up. So that's basically the bottom line, is that high temperature, low pressure moves components from the oil to the gas phase in general. Okay, so high temperature, low pressure is bad surface separation. Okay? And if you have to have low pressure, you want to have as little gas around as possible, you know, for it to steal the oil components. So it's this number of stages, and so, but this is kind of an aside. This is not really part of what we're doing, but you definitely don't want to use this simply because you don't process at the surface like that.
Why are we not doing this correction for above overboard?
You will, but that correction is trivial. There's no above bubble point data in the DLE. the DLE doesn't, it starts at the bubble point. We have to go to the CCE to correct the higher pressures. Okay. So next we want to know the RS at a given pressure. How much gas is in solution? If we went to 1,600 pounds and we took that oil to the surface process, how much gas would come out of solution? Okay. So there's also an equation that can be used for this, and it's RSB minus RSD at the bubble point minus RSD at our pressure times BOB over BO differential at the bubble point. This is the same number here. Okay. So just to do our example at 1,600 pounds, the RSB, of course, that was 768. RS differential at the bubble point. That's from the table up here. That's the 854 number. 854. And that's per residual barrel. Okay, and then RSD at 1,600. That was 544. And then these are the same, 1.474 over 1.6. So then RS at 1,600 would be the 768 minus 854 minus 544. That same ratio, 1.474, 1.6. If somebody can do that calculation. And this is approximately. It's 467. Okay. All right. Almost nobody does this anymore. Okay, it's okay to talk about it, but and it can be used if the method is okay. You could do like a troll oil field. It's a lot of oil. It's you could use it for troll oil. Probably a lot of fields in the world it can be used. So I'm not going to say it can't be used, but Appendix D, you can study that if you're really interested in this. When I came to Norway in 1978, I was fortunate enough to go to 2 courses, industry courses. The one course was given by Core Laboratories, free to universities and then I think institutions. There were not many petroleum engineers then, so they came and gave the course free because it was part of this thing about getting concessions. Core Labs wanted to build a laboratory, and it was really the only PVT laboratory at the time. And the guy who signed on every report back then in the Dallas Core Laboratory, their main laboratory in Dallas, Texas. His name was Phil Moses. No relation to the Moses. And he actually was at the course during this 3-day course. I think it was 2 days on rock properties and 1 day on PVT. And so it was kind of, I was getting into PVT then, so it was a big deal. I mean, to see this guy in life, I'd seen the signatures before, so it was kind of nice to meet him. He was laid off in one of the low price things in the early 80s, mid 80s. But he told the story that they used to hold these courses for the industry, and he said that he got a phone call from Standing, Professor Standing, who was here. You've learned about the Standing. Standing was quite a course. He was kind of a little bit hard on the people who didn't take engineering seriously. And he said he got a call from Standing once. He says that, I'm going to send my engineers to your PVT course, but there's one thing they better know when they get back. And if they don't know anything else, they better know this. And this was exactly the thing that he was most preoccupied that all the engineers in Chevron were to learn, was that they didn't use the differential BO because it was a bad number. It was a bad process, or the RSD or the BOD in their engineering calculations. Okay? He said, I want my engineers to know how to convert to the proper stock tank barrel basis. And apparently that was the deal, and they sent the people to the course. So back then, this was before anybody was using equations of state, that was the big deal. That was the thing that you had to learn how to use and do properly. And the main thing was to avoid using the differential numbers given in the lab report, because they just are not good numbers. So that's the about everything we need to know about, I think, the differential liberation test. Any questions?
What about viscosity? Is it similar?
Yeah, the oil viscosity, you just use straight because it's measured at pressure and temperature. So basically you get the oil viscosity straight from the report, directly. There's no surface process involved. Nobody asked me about the second course I went to. We'll learn more about that when we finish chapter 7.